Alright, so let's talk about substitution reactions. We really divide this into two groups. There are alkyl substitutions, which means it's really going to be the chemistry of alcohols and, more importantly, of alkyl halides. You can also have acyl substitution, which is typically a second semester reaction mechanism, where you have a carbonyl with a good leaving group. For example, an ester would be an example. So this is where we're going to focus our efforts right now, are on the alkyl substitutions. Substitution reactions will always involve two mechanistic steps. One will be, of course, a nucleophilic attack. And number two, it will involve loss of a leaving group. Now, if you think about all the logical possibilities that these two patterns could be expressed, we could have one occurs first, which leaves us with an intermediate, and then the second pattern occurs. We could have the second occurs first, leaving us with an intermediate, and then the first occurs. And the third possibility is first and second occur. A lot of people will use the word simultaneous. I think simultaneous is misleading, but they occur in a concerted fashion. The first possibility is reserved for acyl substitution. So right now we absolutely are going to cross this off the list, but we will come back to it when we start talking about carboxylic acid derivatives like acid chlorides, acid anhydrides, esters, amides. The second possibility is the SN1 mechanism. And in fact, the intermediate is a carbocation. The third possibility is the SN2 mechanism. So arrangements 2 and 3 are going to result in alkyl substitution. So let's examine propyl bromide as our substrate. In every substitution reaction, we will have a substrate, we will have a nucleophile, within the substrate, we will have a carbon that is bonded to a really nice leaving group like bromide. This is going to be our electrophile. And the halide itself is the leaving group. I'm just going to abbreviate that as LG. So regardless of whether it's SN1 or SN2, I will have a nucleophile reacting with a substrate to produce a new compound. I'll make a carbon nucleophile bond, and I will have a leaving group, whether it's SN1 or it's SN2. So the hallmark of SN2 is that this is a little bit of an overgeneralization, but everything happens at once. And when I say everything happening at once, what I mean is bond breaking and bond making while it's an overgeneralization to say they occur at the same time, they're very, very close. So to a certain approximation, they do happen at the same time. So if we were to look at a mechanism, an arrow pushing mechanism, for SN2 it's very simple to draw these arrows. As this process is occurring, this process is occurring. So here's my loss of leaving group. Here's my nucleophilic attack. Now this means this reaction is one step. That's not always the case. If I had to protonate an alcohol, for instance, that would be more than one step. But only SN2 has the possibility of occurring in one step. So let's take a closer look at the kinetics. Let's actually see why this is called SN2. So if, again, we start with the premise that this occurs in one step, then the kinetics of this reaction would be the reaction rate is equal to the rate constant times the concentration of the nucleophile times the concentration of the substrate. In other words, it would be first order with respect to the nucleophile and first order with respect to the substrate. So the kinetics is second order, just add the exponents, overall. SN2 stands for substitution literally one atom or functional group is replacing another in the molecule. So the nucleophile is swapping positions with the bromine. The N is for nucleophilic. Notice reactions are typically, in organic chemistry, they are typically describing what the nature of the other reactant is besides the major organic product. We saw with electrophilic addition that the organic reactant was a nucleophile, but something like Br2 or HBr or OSO4 or any multitude of reagents, MCPBA, were all electrophiles. Now this is called a nucleophilic substitution because the compound other than the organic compound is the nucleophile. And of course the 2 means second order kinetics. A lot of people get confused that the 2 means it happens in 2 steps. That's incorrect. So if I were to map this reaction in terms of a potential free energy diagram, here we would have free energy as a function of reaction coordinate. Of course, we would have our reactants. And what I'm going to do here is I'm going to use fluoride as a nucleophile. It's not a great one. Here are my products. There are no intermediates, but there is a transition state. I want to be very specific about this transition state. I have a carbon atom that is bonded to 2 hydrogens. It's also bonded to an ethyl group. And I have a nucleophile that's approaching fluoride. I have a leaving group that is in the process of leaving. That's the Br. Of course, this is partial negative. This is partial negative. Notice I have 5 areas of electron density. We're taught in organic at the very beginning of the course that carbon never makes 5 bonds. Well, bond is a relative term. It doesn't make more than 4 bonds and is stable, but it does, for a billionth of a second, make a transition state where there are 5 areas of electron density. This is a trigonal bipyramidal geometry. The attack has to be from the side opposite where the leaving group is going away, because you're essentially going to have this zone of electron density that would repel electron density from attacking. We call this, quite affectionately in organic chemistry, backside attack. When we have backside attack, and I think what is really useful is if you were to look at the geometry of this molecule before the bond broke. So let's do that real quick. So let's imagine we have, here is our electrophilic carbon, ethyl group, hydrogen, hydrogen, bromine. As fluorine begins to attack, electron density and electron density in the molecule are going to repel one another. And so where these groups might point to the left, so let me draw this just a little bit differently. In the transition state, they're planar, but after I've made the bond, they're going to be flipped to the right. This is called inversion of stereochemistry. And it's one of the hallmarks of an SN2 reaction. Relative to this starting material, this product has inverted stereochemistry. For example, if there is an R chiral center before, we will have net S after. Doesn't mean it's completely converted to S, but we will have predominant S product. Even if there's no stereochemistry, you're still going to have inversion. Almost like when you have an umbrella in the windstorm and the prongs of the umbrella get inverted. That's what happens after nucleophilic attack. And it has to be that way because the front creates an electron zone of inhibition. The LUMO in this molecule is most accessible from the backside. Remember, this is all about orbital overlap anyway. So backside attack is a hallmark of SN2 chemistry. So there's several ways of looking at SN2 reactions. We can look at the kinetics. We can look at the mechanism. We can look at the energetics. We can look at stereochem. We can look at solvent effects. We can look at substrate preferences. We can look at leaving group preferences. These will be different between SN1 and SN2 with the exception of leaving group preferences. Typically, the more stable the leaving group or the bigger the atom, the more reactive the substrate will be. For example, iodide is a better leaving group than bromide, which is a better leaving group than chloride, and F- is absolutely terrible. So in SN2, we know the kinetics. Reaction equals rate constant times the concentration of the substrate, which I'm going to generally represent as Rx, times the concentration of the nucleophile. The mechanism is concerted. The energetics, that's the potential energy diagram. One step with a single transition state. Of course, G is on the y-axis and reaction coordinate is on the x-axis. Stereochemistry, net inversion. Solvent preferences, we prefer aprotic polar solvents. And we'll explain that in just a moment. Substrate, the more bulky a substrate is, the less likely backside attack is facilitated. So a methyl is the most reactive for SN2, then a primary, then a secondary. Tertiaries are so slow, their activation energies are so high, we essentially do not consider those to occur. And a leaving group preference, iodide is better than bromide, is better than chloride, is better than fluoride. Now there are other leaving groups we can have, but the chemistry of SN2 and SN1 is intricately tied to the chemistry of alkyl halides. They are typically our classic examples. Now let's talk for a minute about nucleophile theory. So let's imagine for a moment that I have NaI, sodium iodide, in solution. We have a couple of choices for solvent. I could have something like acetone. I could have something like water. If I have acetone, the carbonyl oxygen is partially negatively charged, and it will begin to sequester integer positively charged sodium cations. So in solution, I will have what we call a naked anion. By the way, that's my nucleophile. So having a solvent like acetone increases the concentration of available nucleophile. And that's important because we've already described how nucleophile concentration is directly proportional to the rate of the reaction. So an aprotic polar solvent would enhance the rate of an SN2 reaction. Now let's compare and contrast that with what would happen when I have H2O. Na plus would be sequestered by the partial negative charge of oxygen. Okay, that's cool. But the I minus is going to be sequestered by hydrogen's ability to form a partial dipole. This decreases the concentration of available iodide, and since the concentration of nucleophile is directly proportional to the rate of an SN2 reaction, it's going to hinder the rate of reaction. So that leads us to a solvent preference that an aprotic solvent, I have 6 carbon atoms in this molecule, none of them are going to have a significant partial positive charge because they're bonded to carbons, as opposed to having a hydrogen bonded to a highly electronegative atom like a oxygen or a nitrogen. So solvents like acetone, and there are some others that we can put in our belt. There is DMF. NN dimethylformamide. All the hydrogens are bonded to carbons. Good SN2 solvent. There is DMSO. We saw DMSO earlier. It's one of the side products in ozonolysis. Dimethyl sulfoxide. All of the hydrogens are bonded to carbons. So any solvent that I have that has all the hydrogens bonded to carbons is a good SN2 solvent. Anything that has a protic hydrogen would be a good SN1 solvent. So we've discussed kinetics, mechanism, energetics, stereochemistry, solvent, substrate, and leaving group preferences. So those are the essential aspects to SN2 mechanism and all of the things that result from that mechanism. So let's look at a synthesis problem. We want to make 3-hexanone. Starting from, and this is a very classic synthesis, ethyne. Now, when he was 17 years old at MIT, there was a young freshman who was taking organic, and he was really bored with lecture. And so during this lecture, when he was 17, he invented something called retrosynthetic analysis. It allows us to work backwards to determine all the reagents and conditions to make this transformation. His name is Elias J. Corey, won the Nobel Prize in 1990 for his contributions to synthesis. And this is what Corey would propose. How can I make this directly from a reaction that we've previously learned? Well, here's what we have learned. That if I have a triple bond, and let's say that we have these two carbons. I have a methyl group attached, and I have a propyl group attached. I can go from this molecule to this molecule by using HgSO4 and H2SO4. Mercury catalyzes hydration of a triple bond. Once it tautomerizes, I have the carbonyl. Now, the next disconnection would be, how about the difference between this molecule and this molecule is in the first step, NaNH2, and in the second step, propyl bromide. And then from here to here, NaNH2 in the first step, and in the second step, methyl bromide, or iodide or chloride. So to convert this to this, these reagents stepwise, then these reagents stepwise, then these reagents stepwise. Step 1 and 2, step 3 and 4, step 5. So if I'm going to outline, once I've worked backwards, now I can write everything forwards like I knew it all along, which is awesome. Start with ethyne. Step 1, NaNH2. Step 2, methyl bromide. Step 3, NaNH2. Step 4, propyl bromide. Step 5, HgSO4 and H2SO4. That's a one-step reaction. And I'll make the target molecule, which is 3-hexanone. Working backwards makes more sense.